And in this week, we have seen plenty of different topics. So I want to start with, how do I? Okay. So I want to start with the global picture of the talk. So long before linear logic, there was lambda calculus. And lambda calculus was endowed with a denotational semantics based on Scott domains and with a theory of program approximation based on Burntree. And then yesterday, Christine Tesson told us that you can also interpret lambda calculus in the relational semantics of linear logic. And Laurent Regnier said, well, relational semantics is just another way of presenting the resource calculus. So today what we are going to see is that you can also see the resource calculus as the target language of an operation called Taylor expansions. That is a different way of having a theory of program approximation. We see that this way is different, but it is strictly related with the theory of Burntree. And we'll also see that we can use the Taylor expansion to prove properties of lambda calculus. Okay, so why do we need all this machinery? The goal is to understand what programs do. And there are nice programs that are very little and understandable. But if I ask you, what does this program do? Maybe you don't know, because it's complex. And so this is why we use, for instance, denotational semantics to interpret the program into a more abstract structure, mathematical structure, that we call a model. And the idea is that since this structure is more abstract, we can then apply mathematical tools to study the programs and the properties of the programs. And, and this must be compositional, so that if I specify the meaning of the primitives of the program, then I can reconstruct the meaning of the whole program. And another way to do that is to use program approximation. So the idea is that you slice your program into elementary bricks that are called finite approximants. And then you retrieve the behavior of the whole program by performing some kind of limit of its approximants. And the crucial point is how to handle recursion, because recursion is the operation that introduces non-termination in a program. So the classic way to do this is to interpret a program as a continuous function. And continuous here means that a finite portion of the output of the program must be generated only by a finite portion of its input. And why? So the key to model recursion is to use fixed points. Because, for instance, if you take this example, you have a function that looks like the factorial, but it is not the factorial because it is not recursive. This is a program that takes a function f, natural number n, and does this, and here it applies f. It is only when you take the least fixed point of this higher order program that you get the factorial. And so if your program is interpreted by a continuous function, then you can apply Kleene fixed point theorem that tells you that you can compute the least fixed points simply by starting from the bottom element that represents the complete lack of information, and then you iterate the function from the bottom element. Okay, so this idea allowed Scott to define the first denotational model of lambda calculus, which is called D infinity. And then some years later, Burntree introduced a more syntactic model. Syntactic in the sense that here the interpretation of a program is a tree, a possibly infinite tree, representing the execution of the program. And this is called Burntree. So to understand the notion of approximation that we want to give, we need to understand what are the possible behaviors of the programs. So a program can be normalizable if after a finite amount of steps, it gives a completely defined result. If it never gives any result, then it's undefined, and we call this unsolvable. But there is something in the middle. Namely, you can have a program that gives a finite portion of output, but then continues with a subprogram P1. And this P1 gives another stable portion of the output, but continues with a subprogram program P2, and so on and so on. So one gets the whole output only if you push the computation to infinity. And this is called solvable. So the idea of a Burntree is to say that the Burntree of a program is bottom if the program is completely undefined, so it's unsolvable. Otherwise, the program gives a finite portion of output and has k sub-programs. In that case, you construct a tree with this portion of the output as a node, and then you compute the Burntree of the subprograms as children. So this might look like an inductive definition, but it is not. Because during this computation, the size of P can increment indefinitely. So this is actually a co-inductive definition. This is why, for example, the Burntree of the fixed point combinator gives an infinite tree. And so if you lived in the 70s, where these notions were introduced, this was scary. And that's why researchers tried to understand what was going on using an approximation theorem, saying that the Burntree of a program can be seen as the supremum of all its finite approximants. So for instance, for the fixed point combinator, you start from bottom, you execute y, and then it gives a little bit of information, and then you continue, it gives another little bit, and only putting all the information together, you get the infinite tree. So in the Burntree semantics, you say that two programs are equivalent if and only if they have the same Burntree. OK, so this theory is very beautiful, but the problem is that it does not generalize to the programming languages that we are interested in, like algebraic, differential, probabilistic, and quantum language. What all these programs have in common is these programming languages have in common is that they can be interpreted in quantitative semantics of linear logic based on vector spaces, and that they can be seen as generalization of the relational semantics morally introduced by Girard in the normal functor power series and lambda calculus paper. In this paper, in the linear logic paper, Girard also mentioned that there is a notion of differentiation which is at hand in these models. And this is a good news, because in mathematics, we use derivative to infer properties of the original function. The derivative measures the rate of change of the output of the function as the input change. And then in this context, you can use the Taylor expansion to compute the best linear approximation of a function. So the question is whether we can import this kind of technique from mathematical analysis to the study of the theory of programming language. And the answer is yes, is what Erhard and Regnier did with the differential lambda calculus. But what we need to understand is what does it mean to derivate a program. So the derivative of lambda x dot m applied to n is simply a program which is linear in the sense that it needs to use n exactly once. So this substitutes n only for one occurrence of x in m, and not for all of them. And so since we have now a syntactic notion of derivation, we can also import the Taylor expansion from mathematical analysis to the theory of programming languages. And the ambitious goal is to replace the old theory of program approximation, which was based on continuity and Burntree, with this newer theory of Taylor expansion, which is sensible to the consumption of resources. So the target language of the Taylor expansion is nowadays often presented as a resource calculus, whose syntax is more or less like the one of lambda calculus, except for the application. You do not apply a term to another term, but you apply a term to a bag of terms, a bag being a finite multiset of resource terms. And the idea is that the bag contains linear resources that you cannot duplicate nor erase. So what happens in the reduction? If we have a lambda x dot t applied to a bag, a single bag containing S1, S2, and S3, morally, you need to substitute each occurrence of S1, S2, S3 for one occurrence of x in t. So if t contains 3 occurrences, this works very well, because S1 goes here, S2 goes here, S3 goes there. But the point is that finite multisets are not ordered. So how do I choose the order in which I'm going to substitute? Since I cannot, I need to introduce formal sums in the system. So if I can sum different programs, then I can consider all possibilities. I take all the permutation, all the possible ways of associating these 3 terms with these 3 occurrences. So you can imagine this sum as a non-deterministic choice, but this choice is never performed. So the sum is kept in the calculus. But then what happens if here I have 3 terms, but I only have 2 occurrences? Where do I put this one? Since I cannot erase anything, the only thing I can do is to raise an error that destroys the whole program. And this is due to the fact that all these constructors are linear. So lambda structure is linear, application is bilinear. So this means that if I have a subprogram that becomes a 0, then the whole program becomes 0. And 0 is the neutral element of the sum, so basically disappear. OK, so in this calculus, you can embed the linear fragment of lambda calculus. So if every abstracted variable occurs exactly once, you just have the old linear lambda calculus, which is not very interesting. Now we can try to construct an unsolvable term. We take omega, which is lambda x dot xx applied to itself. And here we say, well, this lambda x dot xx expects two occurrences of the argument. So I try to put the same thing twice. But when I reduce, I get this. And now this one is expecting two occurrences of the argument, but it gets one. So it goes to 0. So we say that it experienced starvation, is death of starvation. But it can also experience surfeit. So in this case, we are expecting one occurrence of f and 0 occurrences of g. So here f gets x, and this is fine. But here we should substitute y for one occurrence of g, which is not there. So it becomes 0. Notice also that the non-determinism can arise from the reduction. So even if I start from a term which is not a sum of things, when I reduce it, since I have two possible ways of putting y and z into the two occurrences of f, I get a sum of the two possibilities. Okay, I don't expect you to become familiar with the calculus right now, but I'm asking you to remind of its basic properties, namely that so if you have a reduction that goes to a non-zero term, then it means that the t here, the lambda x dot t, must use each of the si's in the bag exactly once during the reduction. Otherwise, the whole program becomes 0. And in this case, if a 0 arises in a subterm, then it destroys the whole thing. And this calculus can be proved to be strongly normalizable. And this is trivial because there is no duplication. And every time you contract a radix, a lambda x disappears. It is confluent, which is also easy to prove because it's locally confluent and strongly normalizing. So you just apply Newman's lemma. And it is linear in the sense that nothing gets erased in a non-zero reduction sequence. OK, so now we can define a Taylor expansion that will be an operation taking a lambda term and giving a power series of resource terms. So the idea is that in an application, m applied to n, we are going to take m and apply it to k linear copies of n. The question is, again, how many copies do I need to give to m? And the point is that it depends on m. We don't know a priori how many times m is going to use n during the reduction to a value. And so we need to consider all possibilities. That's why we take the sum over all possible k's. And here we put all possibilities. But now, since these are multisets, we are counting too many things. So we need to divide over k factorial, just because of the non-ordering within the multiset. So if this doesn't seem like a Taylor expansion, you can see that the same terms written in the formulas of the differential lambda calculus are these ones. And this really looks like a Taylor expansion. OK. Now, to simplify the setting and to make Lionel angry, we are going to forget about the coefficients and just see this as giving a set, a possibly infinite set of resource approximants. So the idea that the Taylor expansion of x is the singleton x. The Taylor expansion of lambda xm is the set of lambda x t, where t is in the Taylor expansion of M. And the Taylor expansion of M applied to n, well, it's what we said before, but now we take t in the Taylor expansion of M and ds1 sk in the Taylor expansion of n, and we take the union over all possibilities. So now these are some examples. We are not going to see them into details, but the Taylor expansion is an inductive definition. And so look that the resource approximant have the same shape as the original term. If the original term is a lambda struction, it will be a lambda struction. If it is an application, it will be an application of things. And basically here we need to specify how many times we take the argument every time we find an application. Also remark that already computing the Taylor expansion of the fixed point combinator is very messy. So this definition is inductive and static, but since the resource calculus is strongly normalizable, we can endow this with a dynamic. So we can define the normal form of the Taylor expansion of a term as the union of the normal forms of its element, because each of these elements is strongly normalizing. It gives a finite sum. We can see this sum as a set, and then we take the union. So now we have two different ways of approximating a lambda term. The first one is to compute its Burntree, and the second one is to first compute its Taylor expansion and then normalize the Taylor expansion. And what Erard and Régnier proved is that these are actually the same. So the normal form of the Taylor expansion of a lambda term is equal to the Taylor expansion of its Burntree. So this relates the two approaches. And the advantages of using the Taylor expansion is that now approximants are closed under application. We can use strong normalization, confluence, and linearity. And we have something that is more easily to generalize to other languages. Of course, where there are advantages, you have also disadvantages. In this case, a lot of indices may arise from the linearization. So in collaboration with Barbarossa, we tried to understand what are the consequences of this commutation theorem for the programs. So the idea is that this commutation theorem has as a corollary that the Burntree and the Taylor semantics coincide. So two programs have the same Burntree if and only if the normal form of their Taylor expansion is the same. How much do I have? 5 minutes? OK. So I'm going to go a little quicker. So what we try to see is whether classic results, fundamental results in lambda calculus that are usually proved either by co-inductive reasoning or topological arguments can be reproved with these techniques. So we consider the contextuality of Burntree, the genericity lemma, which follow from Scott's continuity via a topological argument, and then the non-existence of the parallel law that follows from Berry stability, the perpendicular lines lemma that follows from Kahn and Plotkin sequentiality. So basically all the results in chapter 14 of Barandok's book. It's the Bible. And we have proved that from the commutation theorem, we can reprove the contextuality of Burntree and the genericity lemma with simpler proofs. And this is not particularly surprising, because from this commutation theorem, actually you can prove Scott's continuity. we were more surprised to discover that as a consequence of this theorem, you also get Berry stability and the perpendicular lines lemma. And I say that these proofs are simpler in the sense that we basically use confluence, strong normalization, and linearity. These are the three ingredients of all these proofs that I don't have time now to see. That for so if you want to look at the proof, just read the paper. I do want to give you the idea of the perpendicular lines lemma. So this lemma says that if you have a context, so a lambda term with holes, and you see it as a function from lambda n to lambda, so I take n things and I give a lambda term back. If this context is constant on n perpendicular lines, then it must be constant everywhere. So we do know what is a line in mathematics. For instance, in the Euclidean space, you have these three lines that are perpendicular because basically you have only one component that changes every time. It is a different component. So we can generalize this notion of perpendicular line to lambda calculus by saying that we are considering tuples where at every time we have a different component that varies. Okay? So the known results are that the perpendicular lines lemma holds for Burntree. This was proved in Burntrae's book using sequentiality. And it fails for lambda beta. This was proved by De Vries and Rullis via reduction under substitution. And if you restrict to closed terms, then this property still holds for, this property still holds for lambda beta, and we do not know whether it still holds for Burntree. Now, let's see the idea of the proof using the Taylor expansion. Well, the difficult part of this lemma is to understand why a context can be constant modulo Burntree. There must be several reasons. Either C does not contain the hole in the first place, then it is constant. This is the trivial case. Or the hole can get erased along the reduction. But there are other possibilities. The hole could be hidden behind an unsolvable. Omega hole, it never appears in the tree because omega is unsolvable and everything that gets eaten by this unsolvable. But there is also the situation that the hole is always there in the tree, but it never appears in the end position. And so it gets pushed to infinity. It is there at every finite step, but it does not appear in the end. So the equality of Burntree is equivalent to working with the equality of the normal forms of the Taylor expansion. So if I have a Taylor approximant, and I have a reduction to a non-zero normal form, it can be constant only for one reason, because the hole cannot get erased during reduction because the system is linear, so nothing gets erased along reduction. It cannot be hidden behind an unsolvable because the calculus is strongly normalizable. There are no unsolvables. It cannot be pushed to infinity because it's a finite calculus. And so this context must be constant for the trivial reason that it does not have the hole inside. If it does not have the hole inside, then whatever you put here doesn't change the behavior of that. So if a constant in the Taylor expansion of C is different from 0, then C cannot contain the old. And by using this property, a simple induction of the size of the resource context gives the proof. And this proof does not use at all the fact that the programs that we consider are open or closed. So we also get the last property. The perpendicular lines lemma is also satisfied for the closed-Tor model of the Burntree. OK, so the point is that all these proofs are easy to generalize to other kind of languages, like probabilistic or even other paradigms, like call by value, call by need. And that's it.